Topics: Non-conventional micro-nano manufacturing, abrasive jet micro-machining, water abrasive jet micro-machining, micro-electric discharge machining, micro-wire electric discharge machining, micro-electron beam machining, micro-electrochemical machining, micro-laser beam machining. Non-conventional micro-nano manufacturing. Non-conventional manufacturing processes is defined as a group of processes that remove excess material by various techniques involving mechanical, thermal, electrical, or chemical energy or combinations of these energies. It does not use sharp cutting tools as it needs to be used for traditional manufacturing processes. Suitable for extremely hard and brittle materials are difficult to machine by traditional machining. Abrasive jet micromachining, A.J.M. Abrasive jet micromachining is a process that utilizes small abrasive particles entrained in a gas stream to erode material, creating microfeatures such as channels and holes. AWJM is similar to sand basting but in a controlled manner and fine abrasives. The impact will trigger a tiny brittle fracture, and gas stream will wash away the fractured fragment. A nozzle is used to convert this pressure energy into kinetic energy and also to direct the jet towards work surface at a particular angle, impingement angle. Upon impact, hard abrasive particles gradually remove material by erosion and sometime assisted by brittle fracture. AWJM utilizes various abrasives including alumina, silicon carbide, glass beads, sodium bicarbonate, etc. Working principle. High velocity, 100-300 m/s, jet of abrasive grits are used in AWJM. Grits are accelerated by dehumidified pressurized gas, 1015 bar. This high-velocity abrasive jet is made to impinge the work surface in a particular direction from a suitable stand-off distance, SOD. High-velocity abrasive jet erodes material primarily by microcutting and sometime assisted by brittle fracture. The abrasive particles from the nozzle follow parallel paths for a short distance and then the abrasive jet flares outward like a narrow cone. When the sharp-edged abrasive particles hit a brittle and fragile material at high speed, tiny brittle fractures are created from which small particles dislodge. The lodged-out particles are carried away by the air or gas. Mechanism of material removal in abrasive jet machining, AWJM, is impact erosion. Mechanical erosion is basically a combination of cutting wear and deformation wear. The wear rate depends on kinetic energy of particles, thus velocity, impingement angle, and also size of particle. Schematic diagram of abrasive jet machine setup. AWJM setup comprises air compressor fitted with dryer and cleaner, abrasive feeder and vibratory mixing chamber, nozzle, well-ventilated machining chamber and various gauges for detecting pressure, flow rate, etc. Components in AWJM. Air compressor. Air is taken directly from atmosphere, it is first dried and made dust-free and then compressed to high pressure. Gases like CO2, N2 can also use. Generally oxygen is not used as a carrier gas. Carrier gas pressure is kept between 1520 bar. FRL unit. Air is passed through filter regulator lubricating, FRL, unit to remove any suspended particles such as dust or oil. Presence of steam in compressed gas is highly undesirable as it can coagulate and can cause agglomeration of abrasives during flow through pipelines. Pressure regulator and flow valve. Compressed carrier gas pressure has to be regulated properly as flow rate is also crucial parameter that can affect MRR. Abrasive feeder and mixing chamber. Fine grain abrasive powders, at ATMPR, at primary chamber secondary chamber to the mixing chamber, low amplitude vibration. Compressed carrier gas is also passed through this mixing chamber and thus momentum transfer takes place between gas and abrasives. The predefined mixing ratio is maintained by the amplitude and frequency of the vibration and pressure of compressed gas has no influence on it. Flow and pressure regulating valves are also employed here to control flow rate and pressure of gas abrasive mixture. Abrasives gain momentum in terms of velocity and start flowing with carrier gas through the pipeline. Nozzle. It converts the hydraulic energy, pressure, into kinetic energy, and thus a high-velocity abrasive jet is obtained. The nozzle is kept at a particular distance over the work surface, stand-off distance, SOD. SOD, inclination angle, the angle between work surface and jet axis, are factors that governs machining accuracy. AWJM nozzle is usually made of tungsten carbide or sapphire, usually life 300 hours for sapphire, 20 to 30 hours for WC, which has resistance to wear. Nozzle is made of either circular or rectangular cross-section, and head can be straight, or at a right angle. Two types of nozzles used in AWJM. Nozzles with round-shaped and rectangular gaped slots. Another classification is right-angled nozzles and straight-edge nozzles. It is so designed that loss of pressure due to the bends, friction etc. is minimum possible. With increase in wear of a nozzle, the divergence of jet stream increases, resulting in more stray cutting and high inaccuracy. Working chamber. It is used to avoid pollution. A vacuum cleaner is connected to the working chamber for removing tiny suspended abrasives from air before discharging it to atmosphere. Process parameters. For successful utilization of AWJM process, it is necessary to analyze the following process criteria. 1. Material removal rate. 2. Geometry and surface finish of workpiece. 3. Wear rate of the nozzle. Effect of abrasive flow rate and grain size on MRR. The following graph shows effect of abrasive flow rate and grain size on material removal rate. MRR increases as abrasive flow rate and grain size increases up to a level after which MRR gradually decreases. Effect of exit gas velocity and abrasive particle density. This graph shows the connection between exit gas velocity and abrasive particle density. If the abrasive particle density is high, then the exit velocity of gas will be lower, which affects the overall productivity of the machining. Both parameter plays an important role in machining. Therefore, optimum level of velocity and density is recommended. Effect of mixing ratio on MRR. Mixing ratio also controls MRR and abrasive flow rate. An optimum mixing ratio will be good for best machining result. Mixing ratio is a ratio that determines the quality of the air-abrasive mixture. It is the ratio between the mass flow rate of abrasive particles and the mass flow rate of air, or gas. When mixing ratio is increased continuously, metal removal rate first increases to some extent and then decreases. Stand-off distance. The influence of stand-off distance on depth of cut is shown in the graph. Depth of cut decrease, sand width of hole increases continuously if stand-off distance increases, but the decrease in depth of cut is only marginal. The major reason may be the deceleration of abrasive particles due to air friction, that abrasive and water drop velocity slightly decrease if stand-off distance becomes longer. In order to achieve a maximum depth of cut, stand-off distance should, therefore, be as short as possible. Working. Dry air or gas is filtered and compressed by passing it through the filter and compressor. A pressure gauge and a flow regulator are used to control the pressure and regulate the flow rate of the compressed air. Compressed air is then passed into the mixing chamber. In the mixing chamber, abrasive powder is fed. A vibrator is used to control the feed of the abrasive powder. The abrasive powder and the compressed air are thoroughly mixed in the chamber. The pressure of this mixture is regulated and sent to nozzle. The nozzle increases the velocity of the mixture at the expense of its pressure. A fine abrasive jet is rendered by the nozzle. This jet is used to remove unwanted material from the workpiece. Why abrasive particles cannot be reused? Abrasives get contaminated by wear debris, removed work material. Abrasives lose its sharp edges and thus reduced cutting ability. If abrasive particles are reused. Presence of agglomerated coarse particles within the abrasive jet. Choking in the pipelines. Faster erosion of nozzle, reduced nozzle life. Unbalanced mixing ratio and flow rate. Fluctuation of striking velocity of abrasive jet, because of jamming in pipeline. Lower material removal rate, MRR. Poor surface quality. More embedded abrasive grits on machine surface. Advantages of abrasive jet machining. Surface of the workpiece is cleaned automatically. Smooth surface finish can be obtained. Equipment cost is low. Hard materials and materials of high strength can be easily machined. It provides cool cutting action, so it can machine delicate and heat-sensitive material. Thin sections of hard brittle materials like germanium, silicon, glass, and ceramics can be machined. Disadvantages of abrasive jet machining. Metal removal rate is low. In certain circumstances, abrasive particles might settle over the workpiece. Nozzle life is less. Nozzle should be maintained periodically. Abrasive jet machining cannot be used to machine soft materials. Applications. This is used for abrading glass more economically as compared to etching or grinding. Cleaning of metallic smears on ceramics, oxides on metals, resistive coating etc. AWJM is useful in manufacture of electronic devices, drilling of glass wafers, deburring of plastics, making of nylon and Teflon parts, permanent marking on rubber stencils, cutting titanium foils. Deflashing small castings, engraving registration numbers on toughened glass, used for car windows. Used for cutting thin fragile components like germanium, silicon etc. Micro-module fabrication for electrical contact, semiconductor processing can also be done effectively. Used for drilling, cutting, deburring, etching and polishing of hard and brittle materials. Most suitable for machining brittle and heat-sensitive materials like glass, quartz, sapphire, mica, ceramics, germanium, silicon, and gallium. It is also good method for deburring small hole like in hypodermic needles and for small milled slots in hard metallic components. Abrasive water jet micro machining, AWJM. The mechanical energy of water and abrasive phases are used to achieve material removal or machining. Fine abrasives, high pressure, high velocity of water jet is bombarded onto the work surface. Potential energy of water is converted into kinetic energy. Erosion will occur if pressure is greater, strength of material. Water is pumped at a sufficiently high pressure, 200 to 400 MPa, 2000-4000 bar, using intensifier technology. An intensifier works on the simple principle of pressure amplification using hydraulic cylinders of different cross sections. When water at such pressure is issued through a suitable orifice, generally of 0.2-0.4 mm dia, the potential energy of water is converted into kinetic energy, yielding a high velocity jet, 1000 m/s. Abrasive particles like sand, SiO2, glass beads are added to the water jet to enhance its cutting ability. In the case of brittle materials, material removal takes place by brittle fracture. Whereas in the case of ductile materials, it is because of the deformation process. The mechanism of material removal is also influenced by the angle at which an abrasive particle or an abrasive water jet hits the workpiece surface, hardness, strength, and other mechanical properties of the workpiece material. Components. Hydraulic pump. It is used to circulate the water from the storage tank during the machining process. The pump delivers water to the intensifier at low pressure of about 5 billion Argentine pesos. A booster is also used which increases the initial pressure of water to 11 bar before delivering it to the intensifier. The figure illustrates working principle of the abrasive water jet machining. The water from the reservoir is pumped to the intensifier with the help of a pump. The intensifier increases the pressure of the water. The accumulator stores the high-pressure water and supplies it at any instant when it is required. The high-pressure water is then passed to the nozzle where the high-pressure energy of the water is converted into kinetic energy. Abrasive such as garnet or aluminum oxide is mixed with water within the nozzle. This high-velocity jet of water when strikes the surface of the W/P removes the material from it. Hydraulic intensifier. It is used to increase the pressure of water to very high pressure. It receives the water from the pump at 4 bar and increases its pressure up to 3000 to 4000 bar. Accumulator. It stores the high pressurized water temporary. It supplies that fluid when a large amount of pressure energy is required. It eliminates pressure fluctuation conditions in the machining process. Control valve. It controls the pressure and direction of the water jet. Flow regulator or valve. The flow of the water is regulated with the help of the flow regulator. Nozzle. It is a device that is used to convert the pressure energy of water into kinetic energy in water jet machining. Here nozzle converts the pressure of water jet into high-velocity beam of water jet. Pressure matters in abrasive water jet cutting, which gives kinetic energy to abrasive particles. In AWJM, the water abrasive mixture consists of 30% abrasives and 70% water in an optimum condition. It is a vacuum chamber where the mixing of abrasive particles into water takes place. The tip of the nozzle, 0.18-0.4 mm, is made of WC, ruby, or diamond to prevent it from erosion. Mixing chamber. It is a vacuum chamber where the mixing of abrasive particles into water takes place. Drain and catcher system. After the machining, the debris and machined particles from the water are separated out with the help of the drain and catcher system. It removes the metal particle and other unwanted particles from the water and sends it back to the reservoir for further use. Part accuracy. Jet drag. Jet curve. Taper. Standoff, NTD. Controlling taper of water jet cutting machine. Working. The water from the reservoir is pumped to the intensifier with the help of a pump. The intensifier increases the pressure of the water from 5 billion Argentine pesos to 3000 to 4000 bar. This high-pressure water from the intensifier is moved to the nozzle as well as in accumulator. The accumulator stores the high-pressure water and supplies it at any instant when it is required. It is used to eliminate the fluctuation of the high-pressure requirement of machining hard material. The high-pressure water is then passed to the nozzle where the high-pressure energy of the water is converted into kinetic energy. A very high-velocity jet of water, 1000 m/s, comes out through the nozzle in the form of a narrow beam. Abrasive such as garnet or aluminum oxide is mixed with water within the nozzle. A mixing chamber is there in the nozzle where the abrasives get mixed with the high-pressure water. This high-velocity jet of water when strikes the surface of the W/P removes the material from it. The water jet after machining it gets collected by the drain and catcher system. Here the debris, metal particles from the water are removed and it is supplied to the reservoir tank. Advantages. It does not change mechanical properties of workpiece, useful for machining heat-sensitive material. It is environment friendly because it does not form any dust particle and used water as cutting fluid. Good surface finish. Cut virtually any material. Cut thin or thick material. It can cut both soft and hard material. Soft materials water jet machining, hard materials abrasive water jet machining is used. It is ideal process for laser reflective materials where laser beam machining cannot be used. Cutting does not produce any dust or particles that are harmful if inhaled. Kerf width in water jet cutting is very small and very little material is wasted. Water jet cutting can be easily used to produce prototype parts very efficiently. Water jets are much lighter than equivalent laser cutters, and when mounted on an automated robot, this reduces the problems of accelerating and decelerating the robot head, as well as taking less energy. Disadvantages. Limited number of materials can be cut economically. Water reactive. While it is possible to cut tool steels, and other hard materials, the cutting rate has to be greatly reduced, and the time to cut a part can be very long. It can also cause a rough wave pattern on the cut surface. Very thick parts cannot be cut with AWJM. Application. Paint removal. Cutting soft materials. Cutting frozen meat. Textile, leather industry. Peening. Cutting. Pocket milling. Drilling. Thanks for watching this video. Please subscribe to this channel for more lecture videos. Until next time. Adios.